Recordings rolling. It's Friday, January 9th. So we have to finish this rotational inertia lab from yesterday. Yesterday we gathered all the data. So we help you guys put together the graph and interpret the graph. Right, so do that in conclusion. Right. AP says AP, just ignore that because of course you guys aren't AP, so don't worry about the AP. So I'm looking to eventually, of course, get you guys the quiz and all this material. I haven't even covered all the rotational dynamics material. Haven't hit angular momentum or anything like that yet. So I need to figure this out over the next couple of weekends. But I think the next quiz I want to have in class, but it won't be until after Martin Luther King Day. All right, so let's go back to this lab. So recap the lab. Yesterday, we had this pipe system. It was free to rotate about the central axis. It could rotate. Remember, I took the arms off and there was almost no inertia at all. It's been really easy. And they attached the arms and now it had some inertia to it, some rotational inertia about that central axis. All right, so wind your string around, hang lab weight over the end, let the lab weight go. It takes some time to fall some distance into calculate acceleration. And that was causing a tension there was a tension in the string at this radial distance around the central pipe, causing a torque, causing this whole thing to not only rotate, but rotate faster and faster. There was an angular acceleration. So we have all these variables floating around. We collected all this data. All right. Also, right before you guys started this, we did look at an alternate way to try to estimate the rotational inertia of the system. You guys remember saying, well, this top bar right here is probably providing most of the inertia, which looks a lot like this one right here. You guys remember that? So we grabbed what's the mass, the length, did 1/12 ml squared, okay, and we came up with this number. And the unit would be kilogram meter squared for rotational inertia. Okay. So I wonder if by the time we go through this whole dynamic process, if it's going to be fairly close to that. Now, earlier today, my other classes, they've been getting numbers closer to like 0.1 to 0.2, somewhere that 0.1. So it's been off by a factor of like 3 to 5, somewhere there. But yeah, but yeah, about the right order of magnitude. So let's try that. Right, so we have all this data here. We're going to do this data. Right, so you guys ready for our next step? Right, let's go over to this graph. Now this graph says torque versus angular acceleration. Right, the title's already there. I'm just writing it bigger for the camera. Okay, and okay, so that's like y versus x. Right, so on the y-axis is torque. So on the y-axis it says torque, and that's in Newton meters. Because R cross F got meters, got newtons. And on the horizontal axis, it says alpha, that stands for angular acceleration, and the unit is radians per second squared. Okay. This whole lab is in base SI units, so all these numbers are already in SI units, so we're good. Okay. And so we need to plot these points, and we're going to have 5 coordinates, because you guys remember we're swapping out the lab weights. So there's 1, 2, 3, 4, 5 different coordinates that are going to plot on this axis system. Okay. Right, so well, I got to scale these axes. So let's find the biggest torque and the biggest angular acceleration, which are both, of course, with the biggest lab weight, which is the very last thing we did yesterday before the bell rang. Guess what? Right, so it's right here. So the biggest torque looks like 0.06 something Newton meters. So I need to scale this axis accordingly. Let's go 0.1, 2, 3, or 0.01, I should say. 0.01, 0.02, 0.03, 4, 5, 6, 7. Okay. So everybody scale their axis here. Let's start at 0, just like we have for all the graphs this year. Go 0.01 Newton meters, 0.02 Newton meters. Right. So the unit that's already embedded in the axis attaches to all these numbers. 0.03, 0.04, 0.05, 0.06. Okay, and then the biggest torque is just a smudge, just a little smidge above that. Right, then angular acceleration. Right, so if there is a torque on something, it will cause an angular acceleration. So just to remind you guys how these concepts are tied together. Okay, you guys remember this poster? Okay, got the wrench in the nut. Okay, and if I push a force perpendicular to the wrench, it causes it to turn. Right, that's a torque. Okay, and a torque will cause something to accelerate in an angular sense. This is Newton's second law of motion, but in a rotational form. Right, think of that way. All right, so biggest angular acceleration I have is right here. It says 0.529, and that's radians per second squared. Okay, so that'll tell me how to scale this axis. So we'll start at 0. Let's go 1, 2, 3, 4, 5, 6. So 0, we'll call this 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. Okay, yeah, and that'll definitely contain all the data. Okay. Right. So all it is, I looked at my largest torque and my largest angular acceleration. Largest torque will tell me how far up to scale the vertical axis, largest angular acceleration for the horizontal axis. They both start at 0, 0. So you guys know every single graph we've ever done in this class starts at 0, 0. Okay? And the axes are scaled linearly. Okay? The exceptions to that rule in the real world, there might be, but in this class, we've always done every single lab graph that way. Okay? All right, let's get these points. So, first one, so small slab weight. So the angular acceleration of 0.055 radians per second squared is right about here. That was caused by a torque of 0.018 Newton meters, which is right about here. So bam. It's a, hold on, wait, is that right? No, I'm sorry. Let me go up here. Oops, ignore that. Right here. Bam. There it is. That looks better. Right. So there's the first coordinate. Do I have a, yeah, little white out on this one? That doesn't exist. All right. Next point. All right, so to get 0.113 radians per second squared required 0.025 meters of torque. That's bam, right about there. Next coordinate 0.246, right about here, and then 0.037 there, bam. Next coordinate 0.344, 0.49, bam, there. And the last one, 0.529, straight up there. 0.061, straight about there. Bam. All right. So you guys got 5 points. 5 points. Now, what do you guys think the overall trend is? Like, what's the best way to, yeah, what do you guys think? Do you think it's a linear relationship, like a straight line relationship?
Yeah.
Yeah, sure is. Sure is. Okay. All right, so yeah, there's a peak here. So the line does fit, which looks pretty much like that about looks like. Right. All right. And you may have guessed that because that's actually related to this green box right here. So torque equals I times alpha. Right. You guys see torque and alpha, that's like y versus x. You guys see it's kind of like y equals mx. Right. Except one more thing. This one actually does have a y-intercept. You guys see that? Okay. Now, I mean, one of the things I want you guys to get out of this class is can you think about like why things work the way they do, right? And I've been getting this y-intercept every class so far, and also year by year. So in the past, this always comes up, right? And it makes sense that it would. Guys, why would there be a y-intercept here? What does this represent?
Starting point.
Huh?
Initial point.
Okay. So some about initial torque. Okay. Plus, yesterday I told you guys to have at least 150 grams. That was the smallest. Right. If we put on something smaller, like this guy's only 20 grams. Okay. If we had hung on this 20-gram guy right here, I'll tell you, the angular acceleration would have been what? Zero. Zero. It wouldn't have moved at all. And it wouldn't have moved at all because there's what in the system? Friction. Yeah, friction. Right. Because no, if this would have been like levitating with magnets in a vacuum chamber, then that would have been gone. Right? But that's not what we had. Right? We had like pipes all put together and they were rubbing against each other. Yeah, guys, this y-intercept here represents the frictional torque that you have to overcome before the system can start rotating at all. So it's really like this. It's kind of like if this is y equals mx, it's really like y equals mx plus b. So it's y equals mx plus b. Now straight from an algebra class. Okay? But the vertical axis is really the torque, and that's well, what do you think the slope, guys? What do you think the slope of this line represents? It's right here. Rotational inertia, I. Yeah, that's I. And then horizontal axis, of course, is alpha. Okay? And then this y-intercept we just talked about, that's the frictional torque. Okay? So y equals mx plus b. Torque equals I alpha plus the frictional torque that had to overcome to start turning it off. All right, makes sense? Right. We just gotta get the slope. This or maybe. Well, ask you guys. Because what are we trying to find again in this lab? What's the whole point of the lab? The question is what? Yeah. What's the rotational inertia? And what property of this graph? See if you guys are following. What property of this graph would answer that question? The slope. Aha. The slope. Okay. So can you guys pick 2 points on the line and do rise over run? Do that. Okay. So I'll do it here. I'll say I, which is the slope of this graph. Well, it would be the change in torque compared to the change in angular acceleration. Is it like rise over run, delta y over delta x? Okay, so we're doing. We're doing delta tau over delta alpha. Same idea. Okay. Now, I'm going to pick, how about these 2 points right here? Is that okay? Point one and point four? Okay. I mean, that's pretty close to the line. Okay, so I'll do that. Point one, point four. Okay. And say, so I'm looking at this coordinate versus this coordinate. You do rise over run. So open parenthesis. I'll write it up. I'm doing 0.049 minus 0.018. That's Newton meters. And then comparator divided by. We're doing 0.344 minus 0.055. That's radians per second squared. So altogether, it comes out to, calculator's about to tell me, 0.049 minus 0.018. Close parenthesis, divide by open parenthesis. Gotta group this together. 344 minus 0.055. All right. 0.107, and the unit is kilogram meter squared for rotational inertia. Okay. And that is the answer to the question we started off with. And that goes in this box right here. 0.107 units kilogram meter squared.
You breathe out.
Yeah. Okay.
Thank you.
Yeah. All right. Okay. Guys, good thing. Okay. Now, if you compare that to the static version that we've got at the beginning of class yesterday, I guess an estimate. Yeah, this is you guys. We got like 0.04 kilogram meter squared. Here's saying like zero point 0.1. So okay, it's off by looks like a little over a factor of two, maybe like 2.5 about. Right. So, okay, but it's about the right order of magnitude. Okay. Also, if you want to see how my other classes did, right here's my period 4 class. Got like about 0.126 kilogram meter squared. And my period 1 class, but we're actually graph came out really nice in my period 1 class. But we did get really large rotational inertia. So interestingly. All right. Right. Everybody get on the lab. Okay. So what you're looking for is right, you have all your data, which of course we got yesterday. You guys plotted the graph exactly like I plotted the graph, and it's line best fit, zip. Okay. You guys got a little map to show the slope of the line, which is what represents the rotational inertia. You guys got all that? Okay. Now, ignore the backside of this page. The backside of this page is AP style lab write-up, but I'm just doing that for AP. So right, we will, and that right there. All right, there you go. Rotational inertia.